Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shazwan and we are from Group 4. We will be presenting about the mini project. These are our group members for Group 4, which is me, myself, Muhammad Shazwan, Teo Mingchi, Muhammad Akil Fitri, Putri Nur Amira Aisyah, and Teo Wei Wen. Okay, so now I will cover about the introduction. What is ECG? ECG is a non-invasive test that used to record electrical signal of heart, and it also helps to diagnose heart conditions. So from this mini project, the objective is to design and implement a conditioning circuit for biosignal with a focus on ECG signals. Next, we will explain also about the methodology, and it is about what amplifier that we will use and the reason why we use it. Next, we will also explain about what filter that we use, and we also do a review on our circuit design and the result of our mini project.
So what is methodology? Methodology is the step-by-step plan we follow to create and test the circuit. The initial step in this project is to construct an electronic circuit design that will be applied to extract the ECG signals. AD20 is used as pre-amplifier while LM741 is used as low and high pass circuit. Advantage of AD620 is precision design for accurate and low noise signal amplification, especially for instrumentation purpose. And advantage of LM741 is widely available and versatile for general applications. So to calculate gain for AD620, we divide 49.4 kilo ohm by the gain resistor RG and then plus 1. To find gain resistor RG, we must divide 49.4 kilo ohm by the desired gain and then minus 1. For example, the gain on electrical signals sent by the electrodes is set to 2. So we divide 49.4 kilo ohm by 2 minus 1, which equal to 49.4 kilo ohm.
Next, bandpass filter. A bandpass filter is a device that rejects frequency outside of a specific frequency range while allowing frequency inside the range. In our circuit design, the filter is designed to pass the frequency from 0.05 Hz to 100 Hz. Bandpass filter divided into two groups, which is low-pass filter and high-pass filter. Low-pass filter allow the signal below cut-off frequency to pass through it, while for high-pass filter, it allows the signal above cut-off frequency to pass through it. Next, for the calculation parts, the bandpass frequency we set is from 0.05 Hz to 100 Hz. According to the formula I shows, df equals to 2 minus r4 over r3. So by substituting df equals to 1.414 as following the Butterworth's characteristic, we can get 0.586 also equals to 293 over 500. So we can get that R4 equals to R8 equals to 29.3 kilohertz, while R3 equals to R7 equals to 50 kilohertz. As we said that the cutoff frequency of low-pass filter is 100 Hz, and by assuming capacitor 3 and 4 equals to 0.1 μF, so by substituting all the values given inside the formula, F equals to 1 over 2 by RC, and we will get R5 equals to R6 equals to 15.9 kHz. And it's the same concept for the high-pass filter. As we said that high-pass filter is 0.05 Hz, and assuming capacitor 1 and 2 equals to 100 μF. So we just substitute all the value and we will get that R1 and R2 will equals to 31.8 kHz. Total gain of whole circuit is G total equals to G preamplifiers times G high pass times G low pass. G high pass and G low pass are the same, which from R4 over R3 plus 1, and R4 over R3 is calculated before 0.586 plus 1. At the end, we will get 1.586. And we just times all the values that we have, and we will get G total equals to 5.0308.
Hi, I will explain the result circuit design for high-pass filter and also low-pass filter. First of all, from our calculation, high-pass filter has 0.05 Hz of cut-off frequency with a gain of 1.586. When we try a very low input frequency, which is 0.5 Hz, we notice that the output from our oscilloscope is unstable. The input and output voltage are displayed in millivolt and the frequency cannot be measured. The gain also has an error. So we are unable to prove that frequency lower than 0.05 Hz are rejected by the practical high-pass filter due to the oscilloscope cannot detect too low input frequency. At exactly 15 Hz, it amplified the signal by the gain 1.574, which is close to our theoretical gain 1.586. Thus, it seems that the lowest frequency at which an oscilloscope can accurately display voltage and output without producing an error is 15 Hz. Next, we increase the frequency to 70 Hz. We notice that the output is stable. The value gain that we get for 70 Hz is 1.528, which is approximate with theoretical gain. The filter keep its approximate constant gain at 1.577 for frequency 110 Hz. When the output is remain steady, it means that it continues to function well and that frequency is greater than 0.05 Hz would pass through. In a conclusion, our practical high-pass filter seems to be consistent with theory even though there are some issues at a very low frequency. Roughly 1.5 Hz is its gain, indicating that it is transmitting the higher frequency as predicted. Next, result circuit design for low-pass filter. First, from our calculation, low-pass filter has 100 Hz of cutoff frequency and gain of 1.5 Hz. The signal was slightly amplified and having a gain of 1.528 at a frequency of 70 Hz. With an output that was stable, it means that the frequency at which the filter starts to allow the output pass-through is 70 Hz. When the frequency is increased above 100 Hz, the output voltage significantly decreases. We may state that the filter starts to reject a particular high frequency. So, to prove that there is a major decreases in the output voltage when the frequency exceeds 100 Hz, we change the frequency to 300 Hz and also 500 Hz. So, at 300 Hz, the gain becomes lower, which is 1.075, and the output is more stable. Lastly, for 500 Hz, the gain becomes much lower, which is 0.529. So, our low-pass filter behaves as we predicted, keeping the high frequency out and letting the lower one pass through. This shows that the practical low-pass filter rejects the frequency higher than 100 Hz by reducing its gain and output voltage, which is obey the theoretical requirement.
Hi, now it's my turn to present about the result of preamplifier. Based on our simulation result, the output voltage is amplified from 2.12 watt to 4.24 watt at 61 Hz. The gain is exactly 2, which is same with the theoretical calculation. This shows that the practical preamplifier successfully obeyed the theoretical requirement. After that is the result of the whole circuit. As mentioned before, the oscilloscope becomes unstable when the input frequency is too low. For example, when we apply 0.3 Hz, the result is fluctuated. Therefore, we are unable to demonstrate that the practical circuits reject frequencies lower than 0.05 Hz. Based on the stimulation result, the output voltage is amplified with gain of 5 when frequency is 50 Hz. When the frequency is increased to 100 Hz, the gain remains stable at 5. However, when the frequency is further increased, the gain drops significantly. For example, when the frequency is increased to 500 Hz, the gain is only 1.692. This shows that the practical cascaded circuits successfully obey all the theoretical requirements. As the conclusions, the ECG prototype was successfully constructed and it obeyed all the theoretical requirements. Thank you.